When your auditors, regulators, and security teams all ask, why should we trust this system? Blockchain alone isn't an answer. In this course, you'll learn how to engineer real, verifiable trust for enterprise and government environments, places where failure really isn't an option. Bringing blockchain into enterprise or government creates a fundamental tension. Technically, code is law. Rules are rigid, automated, and run on decentralized infrastructure that nobody can easily override. In the real world, though, law is interpretive and often reversible, with multiple jurisdictions and regulators involved. The practical challenge is the compliance gap between these worlds. Our aim in this course is to design systems that are compliant by design, not just compliant on paper. In regulated environments, you're never designing against a single rulebook. You're working at the intersection of four forces that often pull in different directions. Data protection and privacy laws emphasize purpose limitation, minimization, and sometimes erasure. Sovereignty and geography impose data residency and export control constraints. Sector-specific rules such as financial crime or health regulations add their own audit and retention requirements. Public sector rules stress procurement fairness, anti-corruption controls, and transparency. Architecturally, your task is to turn these collisions into alignment by making the ledger, identity, and data models compliant by design, instead of bolting compliance on afterwards. Designing blockchain-based trust doesn't mean inventing a brand new control universe. The real question is, how do blockchain's features satisfy controls auditors already understand? Ledger immutability and hashing provide concrete evidence for data integrity controls. Consensus and logging support NIST CSF risk objectives around detection, response, and recovery. Permission participation, PKI, and roles map directly to ISO 27001 access control and to SOC 2 criteria for security and integrity. Your architecture job is translation. Every cool blockchain feature must trace cleanly to a specific testable control. Immutability and the right to be forgotten look incompatible, but they don't have to be. A common pattern in regulated environments is crypto shredding. Personal data stays off-chain in systems that already support deletion. Only a cryptographic hash, a fingerprint of that data, is committed to the ledger. When you must forget a subject, you never touch the chain. You securely destroy the off-chain data or the encryption keys. The on-chain hash remains, but it can no longer reveal or link to any identifiable information. Data residency laws say certain data must never leave a jurisdiction, yet blockchains naturally replicate everywhere. The way to reconcile this is topology control. Treat geography and regulation as first-class architecture constraints. Validators that see raw data are physically hosted inside the required country or region. Peers outside that boundary either see nothing or only redacted views and hashes. Private channels or collections restrict which organizations receive full payloads, while the global network still shares proofs of events. For cross-border verification, zero-knowledge techniques let you prove compliance or attributes without exporting the underlying data itself. Identity is the real gatekeeper of any blockchain-based trust system. In enterprise and government settings, you can't just hand out keys. You need strong vetting through existing KYC, AML, and IAM processes. The blockchain should plug into those systems, not replace them. Once identities are anchored, smart contracts can enforce role-based access control, so who can read, write, or administer the ledger is governed transparently and consistently across all participants. In regulated environments, treating smart contracts as the law is risky. Courts recognize legal agreements and intent, not just solidity code. A more robust view is, code implements the law that's defined elsewhere. The Ricardian contract model bridges this gap. You have a human-readable contract that's legally enforceable, and the smart contract explicitly references it. You also define how electronic signatures are recognized and what happens when execution fails or behaves unexpectedly. As architects, you must design for that linkage, clarity, and fallback from day one. Next, we'll move into the governance charter, the rulebook for your consortium network. We'll examine how organizations join and can be removed, how upgrades and parameter changes are decided, how liability and responsibilities are allocated, and how costs are shared so the network remains sustainable and politically acceptable. In regulated environments, you rarely want smart contracts to be the final word in every situation. You design for a happy path where almost all transactions execute automatically, and a clearly defined escape hatch when something goes wrong. That escape hatch is your kill switch and dispute process. It might pause execution, route a case to human review, or hand control to a traditional legal or mediation forum. Architecturally, you're deciding two things: exactly when automation must stop, and who becomes liable and empowered once the off-chain process begins. Blockchain also changes how audits work. Instead of sampling a few records after the fact, you can give auditors real-time assurance over all records. Every write becomes part of a tamper-evident log, backed by cryptography, not just process controls. That creates a precise chain of custody for data and assets, and a shared, independently verifiable history across organizations, dramatically shrinking reconciliation work and dispute windows. When blockchain data is part of a dispute, the key question is, will a judge or regulator actually trust the record? Evidence and admissibility are about turning cryptographic guarantees into legally usable proof. That usually means three things working together: strong, auditable timestamps, clear binding between transactions and real-world identities, and human-readable representations of the data and processes. Without those, your beautiful ledger may be technically impressive, but not admissible. Think of compliance as a continuous loop that mirrors your technical lifecycle. In the design phase, you decide what risks you're willing to accept. You run privacy impact assessments and choose consensus and data models that can actually be defended to regulators. During build, you turn those intentions into enforceable code with smart contract audits and, where justified, formal verification. In operate, compliance becomes a live activity through monitoring and real-time auditing. Finally, when systems retire, obligations continue: verifiable archival and controlled key destruction. Compliance by design really comes down to 5 habits. First, map your blockchain features to familiar control frameworks so auditors can follow the story. Second, aggressively partition sensitive data off-chain and keep only proofs on-chain. Third, pair every technical rule with a governance charter and legal contract. Fourth, design crypto erasure upfront. And fifth, define clear manual dispute resolution procedures. Designing blockchain-based trust isn't just picking a ledger. You're designing an institution in code. The central question is, which guarantees come from cryptography and consensus, and which must still come from law, regulation, and human governance?